Good afternoon, everybody. Today, I have opportunity to present our ideas on solar thermal energy in couplings with desalination. What we develop is the idea of high thermal efficiency, high recovery, multi-effect distillation system, hybridized with nanofiltration, softening, and membrane distillation IMETS process. I will develop that in partnership with Aaron Mandell, who is co-founder of Water Effects Company, and Dr. Jeff Ong, CEO and founder of IMETS, who is in Switzerland today, or working in Switzerland. The transformation in energy and water sector has begun. So we see a tremendous movements in both the worldwide in water desalination needs.
How are you doing?
Good, how are you?
Hi, everybody. Hi, good to see you, Said. We believe that renewable energy, thermal energy particularly for desalination, can compete with intermittent PV RO desalination systems because of lower electrical energy consumption, particularly for MED, higher recovery and ability to operate basically 24/7. This is an example of the largest thermal installation in Dubai, called Dubai Noor, which is 700 megawatts project combined of solar tower and parabolic trough collector. What is amazing about that project, which is now operational for a few years, that is producing electricity on 24/7 at 7.3 cents per kW hour. Now, PV is obviously very competitive, and Middle East produced the lowest ever energy or levelized cost of energy from photovoltaic at 1.04 in Saudi Arabia on large scale, 300 megawatts. So renewable energy is really becoming not only challenge or use because of carbon footprint, but basically becomes more economical in coupling to industrial and desalination uses. What we have is develop a solution which combines thermal energy with multi-effect, which is then multi-effect with TVC. We have a version of just straight multi-effect, but this one is MED TVC, which uses a remix nanofiltration process for high temperature effect, and bottoming cycle is membrane distillation with a new process called enhanced multi-effect thermal separation process. We are able to achieve in that process unprecedented thermal energy efficiency of 34.1 kW hours per cubic meter and recovery of 95%, emits producing 180,000 milligram of per liter of desalting concentrate from brackish water reverse osmosis, and leads to ZLD with fluidized seed slurry crystallization in Oslo type of crystallizer. What is important that by increasing temperature of MED, we significantly move from current state of art, which is basically in Middle East 65 degrees C, and raise that to 95 degree centigrade. They, on the lower salinity water, their current state of art allows 75 degrees C. By raising the temperature of MED without the risk of scale, we dramatically increase the range and able to increase performance ratio or efficiency, what we call performance ratio from currently about 10 to 19 kilogram of distillate for 23, 26 kilojoule equivalent. And that really results in this 34.1 kWh per cubic meter. We use for that we do not produce power from the process. We're using teaming up with sun vapor, which is using innovating green parabolic trough collector and bullet steam accumulator, which provides us hot water and then converted to steam as 3 bar, which is used now on 10FX thermocompression TVC process. And the brine, the end of the multi-effect, as you will see in a moment on the flow diagram, stops at 80 degrees. But having thermocompression from 80 degrees to 60 degrees to 95, we are able to really compress significantly more vapor than in conventional TVC system. Here is a presentation of the system. Let's see if it works.
Aaron Mandell here, representing the group that's led by Leon Awerbuch. Our proposal is to demonstrate solar desalination on brackish RO, agricultural drainage water, and seawater using a hybrid MED TVC NF process. We're combining solar heat with low energy distillation to achieve high 96% water recovery using 35 kilowatt hours of energy, for a total energy cost of 35 cents per cubic meter to achieve full zero discharge desalination. Here's a quick video of the EMETS process.
This device, it's a new type of thermal water separation system that can be used for desalination, brine concentration, and also for industrial wastewater treatment systems. Desalination currently uses 2 types of technologies, thermal and membrane. For both the technologies, such as membrane, reverse osmosis, the cost is relatively high. Now today, we are taking the best of both worlds, thermal and membranes, and integrate them together to produce an ultra-efficient desalination system that can produce water at a lower cost.
I don't know. Aaron, can you unmute yourself?
Yep, I'm here.
Okay. Why don't you tell you that in broad sense, the ideas which we have between MED, solar thermal, and membrane distillation, which in form of EMETS.
Yeah, so I think the point that I would emphasize here is just that if you're trying to do high recovery desalination, where the energy consumption is going to be quite a bit higher than just traditional water separation, you know, if the energy consumption is, let's say, 35 kilowatt hours per cubic meter, and you can get access to energy at a cost, let's say, just round numbers, 1 cent per kilowatt hour, which is a very good target for renewable energy, you know, then you're already right there at 35 cents per cubic meter, not including anything else, just raw energy cost going into the total cost of water. So it's obviously very critical to make sure that both the specific energy consumption and the cost of energy are very low in order for this type of a process to be economical. And so those are kind of the 2 vectors that we're really trying to optimize here, is getting access to very inexpensive heat to drive the brine concentration, and have as high thermal energy efficiency as possible to get to high recovery.
Great. I think the idea is straightforward, because we are not talking of parabolic trough collector generating power or solar tower. MED, and I will show that in a moment, of current state of MED TVC, can produce desalination water with much lower electric energy consumption than even RO. The most advanced, I will just jump into it, is producing today at 0.9 kWh per cubic meter of electric power requirements compared with the most advanced seawater RO, about 3.2 kW hours. So if you can, as Aaron said, use low energy, low temperature heat for desalination, the thermal MED and MED TVC can be very effective. What you show is flow diagram. I obviously don't want to spend too much time, but the beauty of that is that by softening the feed going to MED high temperatures, we can really move to 95 degrees TBT without risk of scaling. And then we have a next step of softening in a remix process at the end of that. Before we go to EMETs, we soften again to remove from the calcium sulfate carbonate and other bivalent ions, which nanofiltration done pretty well in the past. So I will just continue with the multi-effect is really established now. As you probably know, the largest in the world MED plant is enormous size. It's in Marafek in Saudi Arabia. It's 800,000 cubic meters per day desalination plants, and is operating now for almost 10 years very successfully. It's using 1 kW hours of electric power consumption to run the pumps and the system. So it's incredible. And we have now even in UAE, we have in Fujairah 230 million gallons per day desalination plant. 100 million out of it is in MED 13 RO, is a hybrid system. And in Kuwait, Veolia built a 107 MIGD, all MED plant, and is operating with 0.9 kW hours per day. And the largest plant in the world is, or unit really, is in Saudi Arabia with SWIC, and built by Sasakura, basically 20 MIGD or 24 US million gallons per day unit. And, we have it's very successful, high efficiency IDE technology in China, which operates about a performance ratio of 14 and 15 with dual jet system. So MED is really today really well-established process. And as I see the specific electric power consumption varies from 0.9 to 1.3. And we will introduce some ideas of how to use the steam converted to water to really what we call heat transforming.
And why, others like these large commercial projects haven't explored raising the brine temperature to increase recovery.
Yeah, so you just added to the impact of nanofiltration. So the conventional wisdom of multi-effect system is now on the Gulf water in Middle East is limited to 65 degrees C. And the reason is that all the calcium sulfate, calcium carbonate have inverse solubility. The higher the temperature, the smaller solubility. So MSF plants, which operate now at, let's say, a maximum 110 degrees C, they have limited concentration factor because they cannot go beyond 1.4 concentration factor today. And in MED, because of calcium carbonate and its sulfate, it's calcium sulfate, the limitation today is 65 degrees. And if you are on the Mediterranean side, is basically 75 degrees. So the solution, it limits MED and MSF because of scaling problem and inorganic scale. The NF introduction is really solving the problem because it's a membrane softening technology and it can remove over 98% of sulfate and 70% of calcium, magnesium, all bivalent ions, and leaves only less than 10% of chloride ion in the solution. So by doing that, what we really introduced, and I will show you for a moment the example of real project which we done on MSF, is to introduce two-stage NF design to obtain high recovery rates, and both that helps the MED TVC as well as membrane distillation image process. And we'll talk a little bit about that. What is interesting about that, even if you increase the in second stage salinity is significantly higher and have sulfate raised from 3,400, which is typical for seawater, to let's say 6,700 milligrams per liter, the rejection is almost the same, 99.6% removal of calcium sulfate. And I will show you this typical schematic which we used in the past and trying to demonstrate is really providing softening for the temperature above the current technology. So if you want to raise, you don't need to soften all the feed. You need to soften the feed and even partial softening to feed the high temperature effects. Here is an example of what we done in Sharjah, in one of the Emirates, in the United Arab Emirates. And we took existing MSF plant and softened the feed with 15% softening of the feed. And we were able to raise the temperature TBT to 116 degrees centigrade. In reality, the same plant, without changing a single tube, produced 50% more water. We really looked at the issue of coupling between desalination and solar field. Solar field tends to be interested to be outside the population. It's not at the coast because there's no availability of land anymore for huge, both thermal or even photovoltaic. With photovoltaic, you can obviously drive the electricity by wire. With thermal, it's a little bit more complicated. So what we did, we developed hot water transforming loop, which means that we take the available heat or steam generated by solar collectors and send that all long distance to a temperature of 95 or 80 degrees to MED, flush it off to provide the source of energy, and then return the condensate back to the solar field. By that allows a long distance separation between solar field and desalination, which logically needs to be on the coast. Unless you're obviously talking about agriculture issue, then the issue is much simpler because we are with proximity of agriculture, like in San Joaquin Valley. And Aaron, you can maybe mention your water effects at this point, your experience.
Yeah, my experience is in trying to treat agricultural water in the Central Valley, which is notoriously sort of difficult to treat using desalination because of the silica and I guess a lot of calcium-based salts. But it's the type of application that requires zero discharge because there's no brine discharge option. So any treatment process that's used for that type of an inland application is going to have to go to very high recovery.
Yeah, and as a matter of fact, if you listen to some of the discussion on agriculture today, one of the speakers talking that unless you produce water with GLD at 60 cents and or per cubic meter, then really there's no opportunity to use it. So our target is really to bring that cost of desalinated of agricultural rainwater around 50 cents per cubic meter. All right, so the interesting story with solar geothermal is that relatively, particularly at low temperature, we are talking 95, 100 degrees C and below, is easy to store in storage tanks, and Sunvapor did that in insulated storage tank, in so-called steam accumulator. On large-scale project, we even consider aquifer thermal storage and recovery, which is new ideas coming up and spreading to store hot water. It's used for geothermal effects as well as some district heating in the past. One interesting angle of raising the MEDTVC higher temperature, that suddenly we generated released carbon dioxide, which is normally in conventional system at 65 degrees, it doesn't release enough carbon dioxide. So when they do post-treatment of the distillate, they have to generate carbon dioxide. With higher temperature, we have a breakdown alkalinity. And in our case, we come out with the idea of taking the carbon dioxide, recompress that, recompress and inject that CO2 in the preheaters to reduce scale control or carbonate scale. We eliminate carbonate scale. We tested that in Sharjah on MSF and seem to be working very efficiently. I don't want to. Here is an example of the Sharjah. You can look at that, you'll see that the rejection of SO4, it was 99.5%, and both on the total permeate and in both stages, the efficiency was really pretty much the same. Now, with introduction, what is happening that finally I was working with DuPont in all days, basically Dow FilmTech, to push them to develop high temperature elements, because it really, in many places, the water is hot. I mean, know pretty well Dubai. In Diwa, the inlet temperature of seawater now in summer exceeds 42 degrees, which is beyond the normal wisdom of operating continuously above 40 degrees is the limit. Now, DuPont introduced new special membrane, nanofiltration membrane that now can operate at 70 degrees C, and we still didn't see use of that in desalination, but I hope that clearly will change dramatically if we can demonstrate it in our application. Okay, so let's talk a little bit about IMETS. This is an enhanced multi-effect thermal separation system. Is patented by our partner, originally Mr. Ong. Jeff was working in Switzerland, in Lausanne, and developed the idea and demonstrated that on laboratory scale, as you saw on the video. Basically what it is combination of multi-effect and membrane distillation. So it has both elements. Obviously, it's too difficult to really go into details, but I will just show you a picture how that works. It basically has membrane in the liquid phase, going basically allowing the membrane distillation process, but vapor on the top part are passing through to preheat the feed water. And so it's a real combination. It's increasing dramatically the ability of relatively small fluxes, which membrane distillation offer today with increased using multi-effect process. I think if you get that recording, and I hope they will allow that. I think I posted even the paper on reference. you can really look a little bit. It's really, I don't want to waste too much time on going into details of the process itself. This interesting part of hydrophobic membranes, which he used, that we are even looking now at spiral wound membrane rather than flat sheet, but it really has the feed is preheated in conventional, although he has enhanced condensation tubing, which he developed as a part of preheating system, which reduces obviously the cost. And then you have basically the membrane distillation on bottom part of the process, which allows the vapor goes through the membrane. We also looked at the idea how to deal with conventional power system, and here is the example how you parabolic solar coupling to MED, the hot transformer loop. It basically takes the steam turbine, steam exhausting from the turbine of the solar power plant, condenses that, but it basically allows high temperature back pressure, and that back pressure is then transformed into hot water, which is sent to MED. A flushing chamber flushes the vapor to provide steam for multi-effect distillation. Oh, sorry, I went backwards. And I think I will almost stop. So the solution we have is, in our opinion, provide a significant impact on ability to develop economic solution for using solar thermal energy to desalinate agricultural drainage, concentrate from brackish water or for seawater desalination. The potential is using solar heat with power at 1.5 cents per kW hour, which really, after levelized, the water cost could be achieved at 50 cents per cubic meter for even relatively 1 MGD desalination plants. So with that, I really will stop our presentation and just wondering if anybody has any question, and we can look at that. I can look probably at the chat. There is already one question. No, I don't know if I see it. You guys can Zoom yourself if you have any question and just ask. Yeah, feel free to question, okay? Anybody has any interest in asking or making comments about the thermal desalination or thermal energy, solar energy, or renewable energy and desalting?
Hello.
Yeah, go ahead.
I've done a little bit of looking at solar heat for providing waste heat or just heat in general to desalination. Have you guys considered at all the additional energy that you can get from photovoltaics when cooling them?
So I didn't hear your question very clearly. So, Aaron, did you hear the question?
Yeah, I think she's asking about like hybridized PV thermal, where you actually.
Yeah, no, I mean,
Yeah.
it happened that I do work with one of developments called Desalinator, which is basically recovering heat from PV photovoltaic to, because efficiency of photovoltaic at best is 21, 22%, the rest is heat. So the coupling of PV and having the heat recover, it makes a lot of sense. And they are now demonstrating their system to couple that to MED TVC. So there is a pilot plant of 250,000 cubic meter, sorry, 250 cubic meters per day going on as we talk in Dubai, in Diwa. So yeah, the combination of photovoltaic and MED in a hybridized system makes a lot of sense.
Yeah, good.
Leon, I actually just one question here on your last point. Do you think 1 MGD is practical on the kind of small end of the capacity spectrum?
Yeah, my personal experience is obviously the smaller it is, the more expensive it is to put together a system. And you know, so now the system are so big in large scale. I mean, not in US, but the US we don't have a single distillation plant except the old General Electric, or you know, in cooling tower blowdown, or in oil industry. But in the seawater desalination, or even in brackish water, 1 MGD is relatively small plant. And obviously, if you could centralize and make it bigger, like in San Joaquin Valley, that would make significant impact on economics. The problem is, you know, like you worked with one agriculture, or let's say water, right? Treatment, the Pinoche. How big is the total flow in their company?
Well, no, and that's the reason we looked at that particular application, because they're aggregating very large volumes of ag water. So they can probably do upwards of more like 20 MGD.
Right.
But yeah, when you start to get to individual agricultural sites or individual groundwater wells, you know, that's when you need to be able to go to very small capacities. But I personally think you have to start with plants that are kind of in the 1 to 2 MGD range.
Right. I agree, because you know, all these small plants, I really come with significantly increased price. There's no magical solution. Now, you know, the people talk about decentralizing, but you know, if you look at large desalination, seawater desalination in Middle East, from Israel, Saudi Arabia, Dubai, you name it, the prices are now around 40 cents per cubic meter. And that, you know, it's incredible how far the price dropped in. And, you know, the world record of today, although we're still seeing if that financial closure, is 27 cents per cubic meter in Dubai, in Hussein Aro plant. It's really unbelievable. But, you know, this is huge plants, 60 million gallons. And I'm not talking even of the huge plant in Tawila in Abu Dhabi, which is 920,000 cubic meters per day, basically 200 million gallons per day, imperial gallons. So it's 240 US gallons, huge. But that's what allows them to achieve significant reduction in cost. The same plants, if they were 1 MGD, I doubt it if they will make it less than $1.50 per cubic meter.
Yeah, no, I agree. And I think at those, you know, at those desalination prices, I think you have to realize that the cost of desalination is really no longer the issue. I mean, at those types of tariffs, desalination is very competitive with other sources of water. And I think the limitation for scaling desalination becomes more the environmental impact, which is where I think solar desalination can play a role, because it comes down to more the impact of the energy that's required, and also the impact of the brine discharge.
That's really what is the biggest problem in agricultural issues, you know. So agriculture, to use that, is what do you do with all the salts, and how you achieve economic recovery of water with salts coming out of brine and not able to dispose. So you have to go to 95, 96% recovery to really be able, and then have some use for the salts which hopefully can find some beneficial uses. And, some of us think we can recover magnesium and calcium and make synthetic, gypsum and so on. But I don't think there is still serious developments in that direction. I mean, everybody is working on that.
No, I think in an ideal world, the salts would be a source of value to help subsidize the cost of desalination. But I think there's more work to be done there. Although I think a lot of people are starting to look at it. There's a lot of recovery of minerals, selective precipitation and crystallization of certain things, mining lithium from brine. So I think a lot of people are looking at it.
No question. I mean, and they should, because, that's how the technology will be developed. I think what we really projected with this presentation is that you can achieve high efficiency, which is one of the reasons, you have to have relatively high efficiency of desalination process. So the solar part will be minimized. And if you can combine cheap solar source of heat with MED and membrane distillation, you probably have a winner. And then obviously still is the final how far you can concentrate without problem. And that's where, in my experience, nanofiltration plays a role.
Yep.
All right, I think we probably can see if we can join some other session if somebody else is still talking. Anyway, thank you everybody to join us, and appreciate the interest, and hopefully we will, Aaron, chase the project, and hopefully we will one day see the light of that. You didn't hear that, but one of the developers in California was looking at some new ideas. When we get the recording of that, you'll find these developers who already look at swing, solvent extraction and electrodialysis, reversal, and so on to generate. They are really very much interested to get to ZLD and hopefully selective mineral recovery. Yep. Anyway, that's it. Thank you, and we'll see you soon. Aaron, take care.
Thanks, Leon.
Bye.
Bye.